unit impulse response function. That means the response due to the unit impulse. So you can find out for any magnitude impulse, and then just add for such impulses the response due to each impulses. That means integration over the whole time period. So that gives the convolution integral, which is also known as the Duhamel integrals. And for damped system, undamped system, we have shown what is the expression, and also for special base excitation, earthquake excitation, what will be the expression. So ideally, or strictly speaking, we can obtain for any arbitrary excitation the responses using the Duhamel integral. However, if the loading function is complicated type, okay, so then it is very difficult to perform the integration, okay, and even numerically also it is inefficient, okay. So therefore, it requires some numerical, direct numerical method to solve the equation of motion, like the central differential method. Then I write some name, right? That Newmark's beta method, Wilson theta method, and so on and so forth. So that we may discuss maybe. Let's say let me first finish the. After this, we'll move to multi-degree freedom system. So once the multi-degree freedom system is finished, and if time is okay with us, then we can maybe 1 or 2 classes you can consider that. Okay. But before that, let us discuss about this. Response due to step function mode. So first we will discuss the step function mode. Okay. So what is step function mode? And is the simplest type of loading you can consider. Okay, non-periodic load. Obviously, you can see from the figure that it is not repeating, right? The load is not repeating after certain interval of time. Okay, so this is a simplest case of the non-periodic load. Okay. Fine. So you see, and with the magnitude of P naught, it is continuous, right? And it will continue after the application of the load. Okay, so it is suddenly applied. Okay. Suddenly applied load, and it is continuing for the time. So since we are not truncating somewhere, or we are not considering this load for a short period, so we'll consider damping also. But in the later case, when you will consider this type of loading, right, this triangular just for a short duration, or this rectangular type of pulse, okay, or let's say some sinusoidal, half sinusoidal pulse. So in those cases, the damping is actually negligible. But here we'll you can neglect damping, but here but we will formulate using damping. So our equation of motion, so basically we have to solve the equation of motion, right? Cx dot plus kx is equals to pt. So what is pt here? In this case, what is pt?
P naught.
Not is the pt. Okay, so I will use the classical approach, not the Duhamel integral approach. Okay, so you can do it in your as a homework. That thing you will get the same result. So classical approach will be easy here. So xt is the combination of complementary solution. Complementary solution plus steady state solution, a particular solution, whatever solution. So your complementary solution is minus e raised to zeta omega nt a cosine omega dt plus b sine omega dt, right? Plus what will be the particular solution? Yes, what will be the particular solution here? Come on, what is the particular solution?
So P naught by K.
So particular solution is due to the non-homogeneous part of the load, which is a P naught constant, so P naught by K. Now we apply initial condition, let us say at rest initial condition, at rest, which is common for most of the cases, at rest initial condition. So that at time t equal to 0, x equal to let's 0, and x dot is equals to 0. Right? So if you just put it there and find out a and b, and tell me the final expression xt. So initial displacement velocity is 0, which is most common for the most of the cases, practical cases. The structural engineering application at least. So again I am repeating, we can do this thing by using Duhamel integrals also, and that is actually for your homework. Okay. So whatever expression you get the same expression using Duhamel integrals. Okay. So you have to integrate by parts actually. Okay. So that you can do. Okay. Yeah, so substitute these two initial conditions at t equal to 0. So these are my initial conditions. So what is the xt?
The A equals to minus P naught by K.
I'm asking what is the xt? A, B, you find out and tell me the final expression. Okay, equal to I'm writing here P naught by K, and B will get something and then put it there and tell me what it is. So obviously since A you got P naught by K, B will be also in the form of something by P naught by K, so I can take P naught by K common. Then this will be 1, 1, and then tell me what is this coming. So e raised to zeta omega t, I don't know whether plus or minus, e raised to minus zeta omega and t will be there. P naught by I have to take common, so it will be cosine omega dt. Okay. And then depending upon the values of b, this will come out. So what is this? Just tell me. Okay. P naught by k, so I can very much take minus sign, right? So it's P naught by k. Yes, just fill the box then.
Plus eta omega n by omega d sine omega d.
Sine omega dt. Okay. So that means b is actually, what is b?
Minus
B
P naught by K eta omega n by omega d.
that's very simple. Just substitute there, and so you obtain the responses. Okay, so response due to the step load. Okay. So now we define the terminology which is called the x. So p naught by k is basically delta st, right? That is the static displacement. Okay. So now x by delta st, that is called the dynamic load factor. Okay. So it is something like magnification factor, but here I mean for the this type of loading we are calling this as a dynamic load factor. So that is nothing but 1 minus e raised to what? Zeta omega t, this thing, right? Minus zeta omega nt cosine omega dt plus zeta omega n by omega d sine omega dt. Correct? Okay. So that is the dynamic load factor. Okay. So now if I plot this load factor for different values of damping ratio, so let us see what we are getting. Okay. So this is the dynamic load factor that you already obtained. Okay. So then if I plot for different damping ratio, so you can see it. Okay. So what is the difference of this plot with whatever you have done for the what is called free vibration problem, damped free vibration problem? What is the difference here? Okay. What difference can you see here? So you see as the damping is becomes increasing, so as increase, so is the quickly dies down, the responses quickly. So what is the difference here, this plot and the damped free vibration?
So in that the value was approaching to 0, but in this it is approaching to 1.
Yeah, so the main thing is that you should say like this, that it is oscillating about this new static equilibrium configuration. That is one. one DLF1 means what? That is delta st, right? So this is actually delta static. So new one is that V naught by k. Okay. Okay. So now, so about this thing, it is oscillate and then it is gradually dies down. Okay. So now you see, if you damping equal to 0, right? Correct. So then you can find out what is the response. You can just put zeta equal to 0 and then zeta equal to 0, this should be 1, then it should be omega n, and this part will be 0, so it will be 1 minus cosine omega nt, right? So that will be the dynamic load factor. Okay. Now, in order to find out what is the time at which the maximum dynamic load factor is occurring, so how to do that? So you have to differentiate it and set it to 0. Okay. So then just differentiate this and set it to 0 and find out what is the time. So you want to find out when the time the peak is occurring. Okay. The maximum minimum basically, but we are more interested in the maximum. So as you can see here, so since the damping is there, so it is gradually going down. Okay. And so we are more interested on the first peak basically, right? Okay. Yes, what I are getting? Tell me. So you'll get something sine of something equal to 0. That will be actually equal to 0.
Sir, 1 by omega d into sine inverse of?
Yes, tell me.
1 by omega d into sine inverse of minus zeta omega n by omega d square.
One by.
Yes, sir. 1 by omega d
Huh?
into sine inverse of.
Sine inverse.
Yes, sir.
How the sine inverse? Differentiating sine inverse is coming.
Sir, you asked for the t value at which maximum is occurring, sir.
Huh.
Yes, sir. If we differentiate this and then equate it to 0, the cost terms will get cancelled, and then we'll have only sine term and then a
Yeah.
constant term plus a constant term equal to 0.
Just tell me the sine term. What is the sine term?
So the equation is zeta omega n plus omega d square sine omega dt equal to 0.
So some constant value into sine omega d into t equal to 0, right? Am I correct?
Yes, sir.
Some constant means time independent. Am I correct or no?
Yes, it's coming like this only. Zeta omega square n by omega d plus
So this, so to make set it to 0, so basically this is equal to 0, right? So sine, okay, so for max of this, so what we are getting, the sine omega d, so let us call it a t star or whatever that time is that, so equal to 0, so omega d t star, you can see from the figure actually, we don't have to differentiate it, the values, so that will be n pi, right? Okay, n equal to 0, 1, 2, 3. But if you see, if you put t star, so t star is equals to n pi by omega d. Okay, or you can also write in terms of t by tn because omega d. Okay, yeah. So n equal to 0, right? So n equal to 0 is the that is t star equal to 0. So at that time it is actually the minimum. Okay. So first actually the peak will occur at n equals to 1. Okay. So that is t star is equals to pi by omega t. Okay. So you can see actually from the figure that we have just shown. Where is that figure gone? Yeah. So it is t by tn actually here. The maximum thing is t by tn. If I plot, okay, where tn is the 2 pi by omega n is the natural period of the system. So it will be around t by tn is equal to 0.5. Okay. Yeah, so now you substitute this and tell me what is the value of x max. Okay. X max is equals to xt evaluated at t is equals to n pi by omega, n pi not, so n equals to 1 pi by omega. So that will be delta st into something, right? So 1 will be there, then something will be there.
so minus e to the power minus pi eta omega n by omega d.
Minus is sure?
Minus e to the power
Huh?
minus eta omega n by omega d.
Omega n by omega d, right?
Pi. Pi.
Pi.
Yes.
So all are getting this expression that what is the x max? So I can write omega d is omega n root over 1 minus zeta square, right? So pi zeta pi root over 1 minus zeta square, correct? So all are getting the same thing or not? Just let me know. Yes. So everyone got this expression?
Sir, the minus e per term can be plus or minus, no, sir?
Can be plus or minus means.
Yes, sir. So when we are substituting cos n pi, so if
We are interested on the first peak, n equals to 1. T star equal to, I have written here, you see the screen. T star equal to pi by omega.
okay, sir.
N
Okay.
equal to n equal to 0, we'll get minima. Time 0, right? That will get minima. You can double differentiate it and see where it is minimum, maximum coming, but you can just easily visualize that.
Okay, sir.
N equal to 0 minima is there, n equal to 1 there is a first maximum actually, the first peak that we are, and that we are interested. After that we are not interested because damping will always going to dies down. Okay, or even damping is not there, the peak will remain the same. So n equals to 1 we just take it, right? So in that case T star is equal to pi by omega. Substitute
Okay,
T
sir.
star pi by omega d here and tell me what is x max. Is it correct? What someone told?
Yes, sir. Same thing.
It's correct, right? Anybody else? Anybody else, please? Let me calculate it. Something is not looks okay here. So what is xt? It's p naught by k 1 minus s2 minus zeta omega nt cosine omega dt plus what is there? Is anything? Omega n by omega d zeta omega n by omega d sine omega dt. So I want to find out at t star is pi by omega d. Pi by omega d cosine phi plus zeta omega n by omega d sine pi, right? Correct? Now tell me what is there. Are you doing like this or something else? So you want to find out. Come on, please. Now tell me what is the.
So it will be p naught by k into 1 plus e power minus zeta omega n by omega d into p.
Why someone told 1 minus? What is the difficulty in calculation? If yes, is it mistake or something else?
Yes, sir, by mistake.
Yeah, 1 plus. So it is 2 minus zeta omega omega will cancel out zeta phi root over 1 minus zeta square. Okay. Now substitute zeta equal to 0. So for undamped case, so what is xt max? So for if we substitute zeta equal to 0 here, what will happen? What will be xt max?
2 p naught by k.
And this thing also you have learned, I think, in your solid mechanics or in your mechanics, whatever, or some initial structural analysis courses, that if you sudden load applied suddenly, then it will be twice that is the static displacement. Correct? Okay, but since the damping is there, actually it will be actually lower than that too. Okay. Okay. Got it? So let us see the plot. Okay. What is that plot about? Yeah. So if I plot x max by p naught by k, that is a normalized one I am plotting. Okay, delta st. So as I told, zeta equal to 0, x max is 2 p naught by k. So suddenly applied force produces twice the deformation it would have caused by the slowly applied force. Okay. So you see, if your damping ratio is 0, so that means when you study that thing in your solid mechanics, that the suddenly applied load will produce the twice that of the slowly applied load. So that is actually you are not talking about the damping which is present in the system. Okay. So even if you see small amount of damping also will create less than 2. Okay. And as you can see, the very high damping which it will just asymptotically goes to, but for very high damping, okay, varies to 1. Okay. Okay. So that is the thing we want to discuss. Yeah. So as I already told, so it can be obtained, right? You see the note. Okay. So you can do it as a homework. So the response that you obtained, right? So that means which one? So let me go back. Yeah. So this expression, right? We obtain using this thing, right? Our classical approach, the complementary solution plus particular solution. This is complementary, this is particular. Then you have at rest initial condition, you substitute, you obtain A and B, and then you obtain this, right? Okay, damped system. Okay, you can substitute Z equal to 0 for the undamped to get the response for the undamped system. So this thing can also be obtained, okay, by considering the Duhamel integral approach. That is this, you have to perform this integration using by parts. Okay, so that you can do and check yourself that whether you are getting the same result or not. Okay, right. And obviously the response that I plotted, so zeta in the, that is the damping ratio, determine the amount of overshoot and the rate at which the oscillation decay. Obvious, right? So the at which it is decaying. Overshoot means what? Overshoot means basically this above this how much it is. Okay, that is called overshoot. So that means if you see the response plot from this static equilibrium position, so that is DLF1. So this much is called the overshoot. Okay? So obviously if the damping is more, the overshoot is less. Okay. And eventually the system settle down to the static deformation. Okay, fine. Now the next type of loading. Okay, so response to ramp function load. Okay, so ramp means like this. So it is actually going for infinite time, but we are obviously not interested that, because for after certain time actually the load will be so much that the system springs and damper will not behave in a linear manner, and then the thing will be different. Okay, so that we are not considering. We are saying that the P naught will be limited to in such a manner that all in the linear elastic region. Okay, that we are considering. Okay, so ramp function with increasing the load increasing linearly with the time. Okay, so here we will not consider damping because we are just cutting it down, truncating it down. We are saying that the TR, okay, the TR is the rise time. TR means RM indicates rise time. Okay, so at time TR it is just till PR. Okay, we are not going further. Okay, and that we are considering this is a short duration. Okay, so we will not consider damping. So as we will see later also that just shown on graph. Okay, so that is available in the books also. You can see that the effective damping is not that much. Okay, and it is better to be on the conservative side during design to ignore the damping, especially in this case of this shock type of loading for a small duration loading. So as we'll see later. So what is the PT at any time T? So P naught T by TR. So anytime tau P tau is P naught into tau by TR. Correct? Simple, right? So at TR time it is P naught. So anytime T is P naught by TR into T basically. Linearly varying damping. Okay. So now you can proceed in a similar manner, but in this case the Duhamel integral will be much more convenient. Okay, so you can just show the equation we are going to solve is that k into x is equals to pt. So pt is p naught t by tr. Okay, correct. T less than equal to tr. So what is the response here? So you just apply. You already know it, right? So you just apply Duhamel's integral and find out xt. Here it will be much easier because damping is not here, so the integration will not be much difficult. So m omega n integral of what? P tau, what is that? E raised to is not there, sine omega n t minus tau d tau, right? You remember the expression that Duhamel integrals or like the convolution integral? So it will be m omega n. Okay, so integral of p naught t by not t, sorry, tau, right? Tau by tr sine omega n t minus tau d tau. Perform the integration and tell me what is xt. So P naught is constant, right? So P naught will come out. Okay. Then TR is also constant. So we are considering it as a certain rise time. So P naught TR will come out. And so that means it will be, I can write P naught m omega n by TR. You can write, right? Wow. Oh, sorry. Trigger of 0 to t, 0 to t. What is remaining? Tau sine omega n t minus tau t tau. And do the integration by parts. Very simple. So any difficulty is understanding what we are doing? We are doing very slowly, and these are typical simple cases. You have already done for harmonic loading, periodic loading. Okay, periodic loading is nothing but is the harmonic combination of so many harmonics, right? Sine, cosine, and then now we are any arbitrary type of loading. So in that case, we discuss about the step loading. Okay, constant amplitude, the continuous time. Okay, and then ramp load. Okay, in that ramp load which is linearly increasing. Okay, so in the last case that you discussed, since there is damping was there, so the integration will be little involved. So that's why we use the classical approach. Okay, but here it is very simple. So damping is not there, so you can easily perform the integration. Yes, tell me, what is the response? These are very simple integration for you, right? Xt is what? Basically, we are solving mx double dot plus kx equals to p naught t by tr. So solving what we are getting. What is xt? You have done much more difficult integration than this. So please read from some books, okay, that will enhance your confidence and idea also. Okay? And you'll see how they are approaching a problem or how they are dealing. So actually in this chapter there will be there can be many type of shock loading, right? Triangular pulse as I shown, then half sine pulse. All those things we will not discuss. Okay, some I will just touch upon some of them, and you can, if you are interested, you can just look at the books. Any of the books you will find out. Yeah. So what is xt you are getting? Come on. So since we are using this dominant integral expression, so it is understood that we are using at rest initial condition, right? Because if there is some initial condition, then you have to add it with that part. But since we are considering at rest initial condition. So what is xt? Come on. Very difficult to integrate. What? Damping is not there. So if damping is there, how will you do it? So the homework I have given, please do it. Okay? And check whether you are getting the same result or not that you have obtained using the classical approach. Okay. Yeah. Anybody else please is good in integration? So I am writing again here the expression for your convenience: m omega n integral of 0 to t p naught T by TR. That is your normal integral, eh? P tau sin omega n for undamped system T minus tau. What is that xt? Please.
So P naught by K
Not K
into
into
1 minus cos omega t.
1 minus
Yes, sir.
1 minus cos omega. Where is omega is coming? Omega n you say?
Omega n. Omega n.
Omega n.
T.
Finish. Or what?
Yes.
This only. Okay. Anybody else? Obviously, I am not do the integration here. Please do
Divided
it.
by TR.
Whole divided by
Yes, sir.
T. This one, right?
Yes.
Anybody else? This is tau, sir. This is tau. I think here I have written correctly tau. It's P tau. Sir. So all are getting this result, right?
Yes, sir.
Sure. So two people got. Any other people? Yeah. Now you will force me, I think, to do the integration. Right? So let me do first in pen and paper. Three people. How many people are getting the same result? I have already got the first one difference. So minus K, TR. Okay. So then I will do differentiation. Omega n. How is it cos here? I'm already getting sine. Sine omega n t minus tau. Then I can
So I'm
put it-
getting sin omega nt by omega square minus tau by
Yeah,
omega n
100
into p naught by m omega n square tr.
P naught by K into tell me
Sin omega t by omega n square
sine omega nt
nt.
nt right?
Yes, sir. Yes, sir. Omega nt by omega
Yeah.
square.
Omega n square.
Yes, sir. Omega n square minus tau by minus t by omega n.
Outside you are getting P naught by K, right?
Yes, sir.
What I have written, is it correct that you are saying?
I wrote in M omega form only, sir. I didn't convert into P. So I'll just convert into this.
I am asking, what is the expression you are saying? Tell me expression slowly. Eh? What is XT?
Okay.
Yeah, tell me. Yeah, please. Yes, come on. First of all, everybody agree with this expression or not, or some doubt is there with this expression? Any doubt with this expression?
No, sir.
No. So just then perform the integrals. Or my writing is not good, so just say this is 1, this is by am, this is by omega n. Integral 0 to t, this is right, 0 to t. This is p naught, which is constant. Tau by tr is also constant. So p naught by tr is basically outside actually. This is sine, sin, sine. The bracket omega n, this is t minus tau, this is okay. Theta. Okay.
So
This
that
is
only.
Sir, I'm getting P naught by KTR into sine omega nt by omega n minus t.
P naught by KTR
Into sine omega nt
omega nt
by omega n minus p.
minus t.
Yes, sir. Minus t, and in that sine omega n by omega n, sir.
This one.
Yes, sir.
Somehow it is coming correct, like it's P naught by K, so I can write T by TR, right? T by TR, but I don't know, minus plus, maybe some mistake is there. But anyway, so I can write sine omega n t divided by omega n TR, basically, right? Okay. So all are getting this thing. It is somehow correct, but sign maybe something is there. Anyway, just let's see what is the response and how it is. Okay, because the time is running. Okay. So basically, if you do it, you will get this thing. Okay, very simple. Just you will take tau outside, then you do the integration. Just integration by parts, two parameter, right? Tau and this thing. That's all. Two parameter. You consider this as uv, right? So you know how to do the integration by parts. So this can be also written as this. So since P naught by K is delta st, so this is for plotting convenience. Okay, this is nothing else. I can write T by Tn, Tn by Tr, because I want to introduce the natural time period of the system. Then I can write omega n equal to 2 pi by Tn, right? Here also same thing. So that means there are two ratios coming into the picture, T by Tn. Okay. So that is the time with, related to the time period, natural time period of the system, and then Tr by Tn, that is the right time by the natural period of the system. So if you plot it, you will get this. Okay, x by delta st by t by tn will get the, it will oscillate, system will oscillate with the static solution. Okay, so you can just see, plot it and see. Okay, so those who are not able to do the integration, please do it, or you can do it in the classical approach also, no problem, but this is very straightforward. Okay, and in fact I can easily, for the first one can be easily done. You see, so p naught by m omega n tr, right? So go to the first part integration, so I'll keep the tau outside. If I do the integration of that, so what will happen? So it will be cosine omega n t minus tau by omega n. It should be minus sign will be there, but since t minus tau is there, it will be this thing. Okay, am I right? So this should be 0 to t. So that is actually the first part. So if I put tau 0, so this is vanished. So if I put t, that will be t by omega n cosine tau equal to t cosine 0, right? So 1, so t by omega n. Correct? This is tr. So omega n k omega n square, so p naught by k, and then bracket t by t. So I already got the first part. Okay. So you can do the second part, that is the d tau by d tau, then those things, right? By parts integration. So I don't know why he has got minus sign, someone. Okay, for the first part. Okay, so I already got, this is this. Okay. Okay, so have you done something mistake, right? You are doing, but this is straightforward. Clear? integration by parts. So you please do that thing that I told, this one. Okay. So for the step load, step function load. So xt is this integration by parts, and see whether you are getting this result or not. That is equation 12. You should. Okay. So I'll stop it here. Next time we'll discuss about the ramp load, but with finite rise time, because you see, I mean, this type of load that we have discussed, right? It is impossible in practical, right? Whatever fast you put, you cannot at zero time, you cannot just give a load. There is some load time is required to reach that load. Okay? So ideally, I mean, practically speaking, it should be something like that, right? So there will be some rise time, some time will be there to rise to that position, and then it can come. It is acceptable. So we'll consider this loading in the next class. Okay. So as I already mentioned to the CR, so I think 6 to 8, right? Your first assessment is there as per the academic calendar, 6 September to 8 September. Okay, that is next week, I think Monday, Tuesday, Wednesday. So please let me know one day so that I will conduct one quiz. Okay, it will be for 15 mark. Okay, through MS form. Okay, so you have to just choose the correct answer. But be careful about that because the time is fixed. So if you submit after the time, it will not accept it. And I have given enough time, okay, because 30 minutes is more than enough actually. Okay, so there is one only big question, that is 4 mark question. Otherwise, all are almost short type or very minor calculations. Like, let's say you have to just apply directly the magnification factor formulation or what is called transmissibility ratio formula and to get the result. And there are just some other question which is just only have to think and give the correct result answer. Okay. So just prepare for that. It will be 15 marks. So I am giving 10 minutes more. So I have seen that 30 minutes is more than enough. Okay. If you have minimum understanding of the subject, then you can do it. Okay. But I will give 35 to 40 minutes. Okay. 5 or 10 minutes more I will give. No problem. So please let me know the timing. Okay. So I am okay with any timing. Okay. You can do it during the class because 6 to 8, I think there will not be any classes, including me. Including my classes. There will not be any classes as per the instruction from the Dean Academy. Okay. So 6 to 8, anytime you can do it, but please let me know sometime earlier so that I can accordingly plan my other ones. Okay. So it will be for 35 minute to 40 minute duration test. Okay. So that is each one of marks 15. And the syllabus will be whatever we have discussed, let's say today, or maybe today is not required, maybe in the last class. Let's say today whatever we have discussed in today from the beginning. So any question?
No, sir.
So total number of questions.
Huh?
So total number of questions.
Total number, how many I have? I think 10. 10 question, 15 marks. So what I remember, some question may be 0.5 marks, some may be 1, some may be 2, or one question I have given, that is 4 marks. Like that you have to solve. But not a big thing. And those type of solving, so I am giving you hints that those type of problem we have already done in class. Okay, so that's one hint I have given. Clear?
Yes, sir.
So my request will be to give the exam in an honest manner by following all the academic ethics and integrity. Okay. Don't go for any malpractice like sharing your answer with others. Okay. So that will eventually you see that will affect your grade. Okay. Because that is just a tick mark, right? So what will happen? So you have given you have, let's say you have told answer of one of the question, just only one of the question. So here someone has done it correctly. Then you have missed and wrongly done one question, but he or she has done that correctly from somewhere else or by his or her own. So ultimately he will get the more marks. Anyway, that is up to you. Okay. So if you have any doubt, you can ask me as I already told, and I have uploaded the tentative course content. Right? Although till now there is no meeting was conducted, but still I have uploaded, and that will be most probably remain as it is. Okay. So actually my plan is to this week there are 2 classes remaining. This week I am going to finish the single degree of freedom system. Okay, so 2 class will discuss more about this impulse type of loading. Okay, then we'll finish the single degree of freedom system, except one topic is remaining, that is what is called the numerical method, solution using numerical method, that will take up maybe after finishing multi degree of freedom system. Okay, okay, fine.